We discussed about first law as well as thermochemistry. Now let's get into the second law. So to discuss second law, we need to understand basic terminologies like entropy and all. Okay. So this is where we'll focus. Check. Entropy is another state function, just like any internal energy or enthalpy. We have this one more uh, parameter known as entropy. It is mainly used to measure the randomness, okay, randomness of a system. If there is some particles or anything that is present within the system, how much is its randomness? That is what is going to be measured. Mathematically, it is defined as any change in randomness, or what we call it as the entropy change of a system, is equivalent to the amount of heat that is supplied reversibly to the system at a constant temperature. Okay, so this is what it read. So, how much amount of heat that is being given to the system, right, at a constant temperature. That heat by temperature will increase the randomness of the system, and which is what we measure as change in entropy. Okay. Now you notice that as the temperature increases, entropy change decreases. This delta S value decreases. Okay. It meant something like this. Suppose if you have water at 10 degrees and then you are increasing its temperature to 20 degrees. Got it? You're trying to increase the temperature to 20 degrees by providing some heat to it. Okay. So in that case, from here to here, as you start increasing the temperature, the entropy will start increasing. So now between these two, if you have delta S1 change, and the same thing between 20 to 30, the entropy change is delta S2. Then one thing we can say, the change in first case will be greater than change in second case. So entropy change at a lower temperature will always be more than entropy change at higher temperature. Okay, clear everybody? Now, let me remind you, just orally remind you, what were the limitations in first law? Okay, first law would tell us how the energy transfer is happening, but there is no comment on how much is the extent of the process, how much is the extent of changes that is happening, and what is the direction the change is happening, whether the overall direction is from system to the surroundings or surrounding to the system. This direction and extent is not something which we can comment based on first law. Okay, but second law mainly emphasize on this part. Okay, second thing, you need to understand one terminology called what is a spontaneous process. Okay, now listen, if any process is placed under a condition, you know uh, it could be spontaneous based on certain conditions. Okay, first, if the change occurs something on its own, we are not intervening, there is no change or there is no external parameters which are trying to help it to change. If the change is happening on its own, that means it is going to be spontaneous. Okay, for instance, if I take a glass of water, correct, if I take a glass of water here, right, and this water is at 10 degrees centigrade. Okay, what is the chance that you know it will start forming ice? Okay, or it will start increasing its temperature to, let's say, 20 degrees, considering outside atmospheric pressure is 40 degrees Celsius. So chances are this direction it is going to be more observed as compared to this direction. Clear? Because external temperature, I mean the surroundings temperature is more, which means more likely the water will try to gain more energy from the surroundings and try to increase its temperature further. Unlike, we cannot expect that at this particular conditions the water will try to form ice on its own. No, unless we continuously keeps decreasing the temperature and bring it to 0 degrees and below, then only this water will start converting into ice. Otherwise, this direction is called as the spontaneous process direction. This direction is called as the non-spontaneous direction. Okay, process direction. Clear? In fact, all natural process that happens on their own, they are all spontaneous. Okay, so this is one important definition we should understand. Clear? Second thing, whenever there is an entropy change which we are saying, if you are saying the entropy change is for system, certainly there is some entropy change happening even for surroundings. Okay, and you will notice that delta S of the system is equal to minus delta S of the surroundings. Okay, which means delta S total is equal to 0. In fact, delta S total, right, it meant that any total entropy change is always sum of how much is the entropy change of the system and how much is the entropy change in the surroundings together. Okay, if a process is happening reversibly, it meant that whatever the system's entropy has increased, it means the same amount was decreased in surroundings, and vice versa. If systems entropies decrease, which means surroundings entropy has increased by same amount. But if it is irreversible, we cannot say this. We cannot say that both of them, the change magnitude is same. So it might happen that systems entropy is more changed compared to that of surroundings entropy, right? Therefore, but one thing is for sure, if it is irreversible process and it is spontaneous, in fact, we learned that irreversible processes are spontaneous. For spontaneous irreversible processes, one thing you will notice that delta S of the total will be greater than 0. Okay, it will always be greater than 0. Clear, everybody? Right. This is the basic idea we should have first. Okay. Now, what does second law of thermodynamics suggest? See, there are many definitions which explains the second law of thermodynamics. This is one of it. Entropy of the universe keeps increasing spontaneously for a reversible for an irreversible process. So whenever there is a spontaneous change of an irreversible process, which meant that the entropy of the universe is increasing. Either the system is increasing, surrounding is decreasing, or surrounding is increasing and system is decreasing. But in either ways, the sum of those two will always be greater than 0. This is what is second law of thermodynamics suggests. Okay, this is one way of looking at it. Clear? Now, let me explain this factor using the best example possible, which led to the definition of entropy in the first place. The idea of entropy came from this particular concept, the concept known as heat engine. Okay, the concept is known as heat engine. Clear? Now, what does heat engine means? See, heat engine means there is an engine here. Imagine the system which I have wrote is like a engine. Okay, and then you are providing heat to that engine, correct? So if you have to provide heat to this engine, obviously the temperature at the source should be higher so that the heat can be pushed into the system or heat can be pushed into the engine. Got it? So the heat that is getting into the engine or into the system, I will write it as Q in. Okay, and temperature at which this transfer is happening, let us call it as T1. Okay, in physics you will use the terminology as QH and TH. The H represents hot reservoir. Hot reservoir is nothing but source. Got it? H means hot, right? So it is the heat is coming from a hot source maintained at a temperature TH. Okay, in chemistry we simply write it as Q in because it is the heat that is going into the heat engine at a temperature T1. Now what happens to the heat engine? Heat engine accepts that heat, try to convert that into work. Okay. So the first steam engine, if you remember, right, it starts moving because it accepts that heat and converts that heat into work. That's how it starts moving the wheels. Okay. So imagine it started converting into work. Clear? And as it starts converting into work means wheels are moving. Clear? But problem what happens, if it has taken this much amount of heat, the heat engine can never convert all the heat into work done. Some of the heat will always be lost. Okay. The lost amount of energy will be in the surrounding, and the surrounding is what we call it as sink. In chemistry we call it as sink, in physics we call it as cold reservoir. We call it as cold reservoir. So here you can write it as QC. That means it is going, some heat is lost towards the cold reservoir, okay, or lost towards the sink. And the sink is maintained at temperature T2, or you can write the temperature TC. Okay, clear? This is what you usually expect. There isn't any engine which can convert the entire heat that is given into work done. Okay, so from here, what are the things we should know? Anything that is conventional in chemistry, anything that is coming to the system is positive. Anything that is going away from the system is negative. Is that clear? So I can say that Q in or QH, both of them are positive. Q out or QC, both of them are, I mean, this is negative. And work done by the system is negative because it is done by the system. Okay. These are three important things we should know. Okay. So from here, I can say one thing, that whatever the heat that is being supplied here, see, Q, okay, QH plus QW, that is actually making the work done. Okay. QH plus QC. Okay. QH plus QC. QH means it is a positive value. This is a negative value. So obviously the difference between these two is what we get it as work done. Clear? Now here is an interesting part. We define a term called efficiency. This is called efficiency or efficiency of heat engine. What is efficiency of heat engine means? That is how much amount of work that you are able to extract from the given amount of heat. Have you noticed this? Q in plus Q out is nothing but work done. And that work done, that is the work which we are extracting out of the given amount of heat. Given amount of heat is Q in. Correct? So Q in plus Q out by Q in is what we define as efficiency. And therefore, efficiency can be written as 1 plus Q out by Q in. Now notice this one. Q in by magnitude is always greater than Q out. Correct? So Q in is always greater than Q out because you are giving obviously more amount of heat as compared to that of what is dissipated out. It is like this. You are providing 100 kilojoules of heat, out of which 50 kilojoules is converting into work. So other 50 will be of heat that is lost. So obviously Q in will always be greater than Q out. So this value will be positive. Sorry, this value will be a fraction which will be negative here because Q out is negative. So 1 minus something is always less than 1. That's why efficiency of the engine is always less than 1. Okay. Now, this engine is practically, we can do it, I mean, experimentally, we can do it and figure it out as well. That's why if you are representing efficiency in terms of heat exchanges, in terms of how much heat is being given, how much heat is being lost, then that efficiency is defined as practical efficiency. We call it as practical efficiency, correct? In fact, you can define theoretically also. I mean, theoretically, we can uh, calculate the heats and then figure out what is the value here. And practically also, you will notice this. So whether it is theoretical or practical, you can get this formula. 1 plus Q out by Q in. Clear? Got it? Now, there are multiple statements which have been proposed from heat engine. The first statement, correct, which we will be using more often in physics is Kelvin Planck statement. Kelvin Planck statement. So this is an alternative statement for second law of thermodynamics. Clear? It states that it is impossible, clear, for any device, impossible for any device uh, as heat engine, any device as heat engine that, okay, operates, that operates on a cycle, on a cycle to receive heat, to receive heat from a single reservoir, from a single reservoir and produce net amount of work, and produce net amount of work. So it meant that some amount of heat must be rejected at low temperature. Clear? The another alternative way of telling about second law is that heat cannot flow itself from colder bodies to hotter bodies. Okay, from hot bodies to cold bodies it can move, but not from colder bodies to hotter bodies. Okay, so another alternative way of explaining second law is heat cannot, flow itself, from colder bodies to hotter bodies. Got it? Now I said that practically whenever you're representing the efficiency, you have to always represent them in heats only. Practically. Okay? And you know that if it is a spontaneous change, that means it is irreversible always. Now let us come to the next part of it, that is understanding something called Carnot cycle. Okay? Carnot cycle is a theoretical attempt of explaining the second law again. Basically, we are trying to explain heat engines working, right, in an idealistic condition. Got it? And that explanation is done by Carnot cycle. So what exactly is Carnot cycle? Carnot cycle is basically a cyclic process starting from A and coming back to A again. Right? We take an ideal gas having a pressure P1, V1, temperature T1. Right? This is the point where we start. Then we try to isothermally expand it. So A to B is an isothermal expansion. Then we reach to a point B. So obviously the temperature should remain constant. Only pressure and volume should change. Thereafter, from point B, I'll make an adiabatic expansion to point C. Okay, B to C, there is an adiabatic expansion. So whenever you make an adiabatic expansion, all three parameters will change. That's why now pressure becomes P3, volume becomes V3, temperature becomes T2. Okay, thereafter, once you get C, I'll make an isothermal compression to a new point. isothermal compression. In that case, again, temperature should remain constant. Pressure, volume should change. So that becomes P4, V4. From this point onwards, now again you're reaching back to A. That is adiabatic compression. Again, you're performing adiabatic compression. So you got four different points wherein isothermal expansion, then adiabatic expansion, then isothermal compression, then adiabatic compression. Okay. Now notice what are the factors we should need to know. Okay. Can I say that from A to B process, if at all I analyze, A to B there is no change in temperature and we are assuming it for an ideal gas only. So delta U of AB is 0 because delta U is NCV delta T. So delta T is 0 means delta U will be 0. Okay. So that means between A to B, if delta U is 0, work will be same as that of heat with change in the sign. That's it. So W to A, what is the work done, beta? It is an isothermal reversible expansion because I am showing a process curve. It is reversible. So for reversible isothermal expansion, what is the formula? Minus nRT1 ln V2 by V1. And this is work done from A to B, which is also called as heat given from A to B. Okay. Next, Q of A to B is this much. Now I can represent this heat as a Q in. That is, this is the amount of energy that we have given to the system. This is the energy given. Okay. Next, let us analyze B to C now. From B to C, you can see Q is 0. Okay. Because it is adiabatic process, Q should be 0. So W of BC should be equal to delta U. And delta U is NCV T2 minus T1. Okay. Delta U is NCV T2 minus T1. Okay. So this is the second part which we know. Third part, from C to D, again it is an isothermal compression. So delta U again becomes 0. So Q will be equal to minus W. So W of CD from here will be minus nRT2 ln V4 by V3. So this is minus nR2 nRT2 ln V4 by V3. Now, what is the heat from C to D? C to D heat will be equal to minus of W, which is equal to plus nRT2 ln V4 by V3. Correct? Now what happened? This time you see the volume V4 is smaller than V3. So this entire value comes out to be negative. That means heat is going out of the system. And that means it is out, heat out. Have you noticed W? I mean, from A to B process, heat is coming into the system. And C to D process, heat is going out of the system. Now D to A there is no heat because it is adiabatic compression. So D to A again Q is 0, delta U will be equal to W. Okay. And W of dt dA will be equal to NCV T1 minus T2. NCV T1 minus T2. Isn't it clear? Have you noticed something? See, work done from B to C, which is NCV T2 minus T1, and work done from D to A, which is NCV T1 minus T2. Both of them are equal in magnitude and opposite in sign. So these two can be cancelled off when you add the total work done. So in the case of total work done, these two factors will get cancelled off. Okay. And now let's notice this one. Another thing we know that this is an reversible change, right? So these two are reversible adiabatic changes. For reversible changes, we know that this formula is applicable. So at this point C, sorry, at this point B, at the point B, you can see I can write T1 V2 power gamma minus 1 is equal to at this point C, which is T2 V3 power gamma minus 1. Okay, similarly, we can write at these 2 points also. So we can write T1 V1 power gamma minus 1 is equal to T2 V4 power gamma minus 1. Okay. So from here, if you notice that T1, T2 will get cancelled, or you can just divide both of them. So we'll get V2 by V1 is equal to V3 by V4. So which means ln V2 by V1 will be equal to minus ln V4 by V3. Got it? Now notice what is the total work done. Total work done will be equal to W A to B, B to C, C to D and D to A. And you know that W, B, C and DA, these two will get cancelled. BC and DA will get cancelled. So what is left now? Work from AB, which is minus nRT1 ln V2 by V1. And this is minus nRT2 ln V4 by V1. And from there, NR, if at all I take common, I will get T1 ln V2 by V1. Okay. And minus T2 ln V4 by V3. Okay. So from here I can write it as, if at all I take this minus common outside, so it is minus nR ln V2 by V1 into T1 minus T2. Okay. So Q in, because this is the total work done. And how much is the total, how much is the input of the work, the input of the heat? It is minus nR T1 by ln V2 by V1. And now efficiency, how do we define efficiency? That is work done by heat given. So work done is minus nR ln V2 by V1 into T1 minus T2 divided by nR T1 ln V2 by V1. Okay. So now you can see these two factors will get cancelled. NR will get cancelled. What is left is T1 minus T2 by T1. Or I can write it as 1 minus T2 by T1. Now this is the this is the theoretical, I can write it as theoretical uh, efficiency. So efficiency in Carnot cycle. Okay. So please go through it once quickly. If you have a doubt, let me know. If you understand, we'll go ahead. So what can I say? When it comes to Carnot cycle, this is defined only for reversible changes. Within the system, there has to have reversible changes. It is like a heat engine which is always working reversibly. Correct? It is like a heat engine which is under reversible conditions, because heat is coming in, heat is going out, work is also happening. So just like heat engine, everything is happening as per Carnot cycle, except that we can only say it has to be, every process in that which is happening has to be reversible. Okay. So the eta which you found out in terms of temperature, we call it as either theoretical or simply reversible uh, efficiency. Now, if I have a reversible process, that means if the heat engine's efficiency and Carnot cycle efficiency is same, imagine if both the efficiencies are same, which means practically and theoretically we are getting the same value, imagine. Okay. Clear? If we are getting same values here, so what does that conclude? Okay. We know that when it comes to heat engine, we have written the efficiency as 1 plus Q out by Q in. Here it is 1 minus T2 by T1. Okay. So if I bring these terms together, like you cancel off this 1 and 1 here, then I can say Q2 by Q1 is equal to minus T2 by T1. Correct? And if at all I take it to the left hand side, I will get this as Q2 by Q1 is equal plus T1 by T2 is equal to 0. Or I can in fact do one thing, put T2 here and bring Q1 here. So in that case, I can get this as Q1 by T1 plus Q2 by T2 is equal to 0. This is also something I can write. Everybody, please notice this part here. Q1 by T1 plus Q2 by T2 is equal to 0. Okay. Now notice this carefully. Can I write this same formula? Okay. Can I write the same equation this way? Q by T as a factor. Q by T as some kind of a value. Some q by t is a formula, q by t is some kind of uh, uh, some kind of parameter, that q by t from a to b, from a to b, if you go it in Carnot cycle, it is q1 by t1, correct? A to b is q1 by t1, this one, plus b to c, q by t, b to c. Because q is 0, this factor has become 0. And again from q to t, I mean from c to d, that is q by t. This is nothing but q2 by t2. So again this factor exists, but last factor q by t again is 0, because d to a, q is 0. So can I write this same equation as q1 by t1 plus 0 plus q2 by t2 plus 0 is equal to 0. So this is for isothermal, adiabatic, isothermal, adiabatic. Correct? So I got a new factor altogether, which is called q by t. That q by t value in a Carnot cycle, from the start as you come back to the original state, the sum of that factor becomes 0. Now tell me, if a parameter's change becomes 0 in a cyclic process, what does that mean? That means it is a state function, isn't it? A state function will only have its summation over the entire cycle as 0. Got it? So therefore, q1 by t1 plus 0 plus q2 by t2 plus 0, that is equal to 0, represents that, you know, this factor which I'm defining is a state function. Okay, so hence we can see this q by t function is what I'm defining it as ds, change in entropy. That's how we got the idea of what is entropy. So entropy change is equal to q by t. If it is a small change, I can write it as dq by t. And this is only defined for reversible processes. So therefore, ds has to be dq reversible by t only. And summation of ds cyclic is 0. That means it is a state function. So S is a state function and this is the formula. I guess the part is clear, everybody? Okay. Now, let me explain you the second part. You know, when it comes to this, is something which I assumed it to be reversible, correct? So we got one thing. For a reversible process, entropy change of the system, you know, total entropy change of the system has become 0, correct? But now what if it is irreversible process? See, for an irreversible process, you know that eta theoretical is greater than practical. We know this because the work done, right? Work done in reversible, uh, work done in a reversible process will always be greater than work done in an irreversible process, correct? And if I divide it by q here, so q of h and q of h, then I can say reversible work done by qh is always greater than irreversible work done by qh. And this is what is efficiency reversible versus efficiency irreversible. And that's what I have written it here. See, theoretical efficiency is always greater than practical efficiency. That is, reversible efficiency is greater than irreversible efficiency. Reversible efficiency we defined based on Carnot cycle, which is 1 minus T2 by T1. Irreversible, we can write it in terms of Q1, Q2 by Q1. And now, if at all, you can see this Q and Q will get cancelled. So, Q2 by Q1 is less than minus 2 T2 by T1. Correct? This is minus T2 by T1. Okay? And if at all I bring it to the other side here, basically I take Q1 here and T2 here. So, I will get minus Q1 by T1 and here Q2 by T2. Both of them are related this way. Now, if I bring it to the left hand side, I will get this one. Q1 by T1 plus Q2 by T2 is less than 0. Okay, we'll get this as less than 0. Clear? So from here, what are we getting? We are getting something like this. That is summation of this value which we have defined earlier as, you know, summation of, okay, summation of q by t. Q by T is coming out to be less than 0 for irreversible. Acha, what if it is reversible? If it is reversible, it becomes 0, equal to 0, correct? So this is for irreversible, and summation of Q by T earlier we got equal to 0. This was for reversible. Now these two put together, we can write it as a formula, that is summation of Q by T, integral of Q by T will be less than or equal to 0 for a cyclic process. Okay, and this is called as Clausius, Clausius inequation, inequality. We call it as Clausius inequality or inequation. Okay, got it. Now notice ds of the system, okay, entropy change of a system was defined as dq reversible by t. ds of the system can also be defined as dq irreversible by t, but it should be greater than that. It cannot be equal to that. Clear? Because when it is equal means it has to be reversible only. If it is greater than this value means it has to be irreversible heat given. Got it? Everybody clear? So in simple terms, I can write S is, a function of S is a function of disorder. S is a function of disorder. So if disorder increases, which means entropy increases. Okay. Any doubt here? Now notice the last step here. ds system is greater than or equal to dq by t. Okay, what does this mean? See, if dq by t is less than 0, okay, if it is less than 0, that means it is irreversible. Okay, but if it is equal to 0, that means it is reversible. Now q by t, I define it for uh, q by t as define it as a entropy of one particular process. Okay, so if I take summation, then I'll get summation of the entire process. So dq, it is like this: ds of the system will be equal to ds from a to b, ds from b to c, ds from c to d, from ds from d to a, like this. This is the total entropy change. Okay, as per the second law of thermodynamics, what did we learn? That this total entropy change always has to be greater than, the amount of heat that you supplied, dq reversible by dq reversible by t, if it is a spontaneous process. But if it is a if it is a process which is spontaneous but at equilibrium, that means it is reversible, then delta S of system has to be equal to dq reversible by t if it is reversible. And this is another way of representing the same formula. That is ds system is greater than or equal to dq by t. Clear? Okay. Now let us understand case by case. Okay.
Sir,
First, yes, beta. Now notice. Let us start case by case about entropy factors. Okay. First, calculation of entropy, for a change in a system. Starting with first case, which is ideal gas. Ideal gas in a system. So imagine I have an ideal gas in a system. Okay. and I need to figure out what happens to its system's entropy change, surroundings entropy change, and total entropy change. Got it? By definition, ds of the system is always equal to dq reversible by t. As per thermodynamics first law, dq can also be written as, you know, du minus dw. Yes or no? I can write it as du minus dw. So dq can be written as du minus dw. Du can be written as ncv dt, and dw can be written as minus pdv. So that minus minus will become plus. So dq is equal to nc delta t plus pdv. I can use that, isn't it? So instead of this q reversible, I can write this value here. Okay, because see, currently I'm doing it for a very small change. That means assuming it like a reversible change. So ncv dt by t plus p by t dt, dv. Now, if I integrate this on both sides, so ds of the system will be s1 to s2, and that will be ncv dt by t, and nr integral 1 by v dv, v1 by v1 to v2. So if I integrate this one, I'll get this as ncv ln t2 by t1, and on integrating this, I'll get this as nr ln v2 by v1. So this is the formula we'll be using for an ideal gas in a system. Okay, how much is its entropy change if temperature and volume is changing? I guess the general formula is clear, everybody. Okay, so this is the general formula. Delta S of the system is ncv ln t2 by t1 plus nr ln v2 by v1. Now let us start putting case by case here. First case is, what if it is reversible isothermal process? We are taking the same ideal gas, but that ideal gas is in a reversible isothermal process. Now what can we say? Delta S of the system will be equal to d. Just now we have checked it out. This is the formula. Since it is isothermal, there is no temperature change, so this factor is 0. So if this factor is 0, delta S of the system will be nr ln v2 by v1. Okay. And what will be delta S of surroundings? Because it is reversible, whatever the change in system will be, that should be the same loss in the surroundings. So delta S of the surroundings will be minus nr ln v2 by v1. Okay. That is delta S of surroundings. This is system, this is surroundings. And delta S of total will be sum of those two. It has to be 0 because it is a reversible isothermal process. Any reversible process means delta S of the total should be equal to 0. Now, second part is isothermal irreversible process now. So you can see delta S of the system will be nr ln v2 by v1. Okay. Because it is still isothermal. So the T factor will not be there. So this is the formula we know. Okay. Delta S of the system reversible will be equal to delta S of the system irreversible, as long as the final volume conditions are same. Does it make sense what I have written? See, whether you operate a system reversibly or irreversibly, as long as your final destination is same, then the entropy change will be same only. Reason, entropy change is a state function. It only depends on initial and final condition. So therefore, whether you drive the reaction reversibly, whether you drive the reaction or change irreversibly, both magnitudes should be same. Got it? Therefore, I can say that minus delta S of the surroundings is not equal to delta S of the system for irreversible process. Hence, for reversible, delta S of the system is this much, but for irreversible, delta S of the system is not equal to Q reversible by T. Okay. But now for irreversible processes, what about surroundings? Okay. See, let me tell you this one because surrounding I have written it here. So for reversible process, delta S of the surrounding will simply be equal to minus Q reversible by T. This is what we learned. But what about irreversible case? Okay, irreversible case, delta S of the system is also not equal to Q irreversible by T. But now notice this one. For irreversible case, delta S of the surroundings, delta S of the surroundings will be equal to minus Q irreversible by T. Now you might say, sir, how is this formula valid? Let me tell you, when it comes to any change in the surroundings, suppose there is some heat lost in the surroundings, heat gained in the surroundings. Do you see much change occurring in the surroundings? Everybody? In simple example, let's say I took a matches box here. I started just, burning a small piece of paper here, burning a small piece of paper. Now I can say the temperature change because of that burning of paper might affect a small region here where I'm sitting. What do you think? Will there be any change of temperature much in the surroundings? No, not much. Correct? Which means for surroundings, any change that is happening is actually very gradual change, very slow change, a quasi-static change. Understood? Surroundings will always have a quasi-static change, which means the change will be extremely low, small, and it is hardly observed. Which means when it comes to surroundings, correct, you can understand surrounding as same as that of reversible conditions. So there is nothing like irreversible as per surroundings point of view. From system point of view, we have something called reversible and irreversible. But in surroundings, everything is reversible. Understood, everybody? So there is nothing like irreversible surrounding. There is always a reversible surrounding. So therefore, I can say delta S of the surrounding can be written as how much heat which is irreversibly given to the system. So minus Q irreversible by T, because system has accepted positive Q irreversible value. So surrounding has lost minus Q irreversible amount of energy. So that heat divided by temperature, that will give us surrounding entropy change. Okay. Now, what about delta S of the total? Delta S of the total is system plus surrounding. System is NR ln V2 by V1. But surrounding, we just learned it as a new formula, that is minus Q in by T, which is greater than, Q irreversible by T, which is greater than 0. Then, so this is the analogy of thermodynamics of second law, which is delta S of the total has to be greater than 0. Okay. Please go through the irreversible case, everybody. Let me know if you have a doubt. Otherwise, I'll go ahead. Let's talk about reversible isochoric process. In case of isochoric process, there is no volume change. So delta V is 0. If delta V is 0, then this factor in the general formula, this factor will become 0. So the only factor left out is this temperature factor. So delta S of the system will be NCV ln T2 by T1. Delta S of surrounding will be equal to minus delta S of system, which is equal to minus NCV ln T2 by T1. Delta S of the total should be equal to 0. For reversible, there is not much to worry about. System and surrounding will be equal, so total has to be 0. Now the same thing if it is irreversible isochoric process. In case of irreversible, delta S of the system does not change, because as long as the temperature change is same, delta S of the system, whether you operate reversibly or irreversibly, the value will be same. But delta S of surrounding changes. Delta S of surrounding can be now written as minus Q irreversible by T, because you are providing heat irreversibly to the system. System will not understand, but for system it is or irreversible, but for surroundings everything is reversible only. So therefore I can write it as minus Q irreversible by T, and delta S of the total will be equal to greater than 0. Sum of these two will be greater than 0 always. Okay. Now let's see about the next process, which is reversible adiabatic process. Very important process. Okay. See, delta S of the system will be equal to 0 because the Q reversible itself is 0. Okay. It is an adiabatic process, so there is no heat that is to be supplied here. So Q itself is 0. So delta S of surrounding is 0. Sorry, system is 0. If system is 0 and if it is reversible, then surrounding has to be 0 as well. Because any change in system is what reflects as surroundings. And if system is 0, surrounding is 0, then overall entropy change delta S of total will also be equal to 0. And it is a process where the entire system is operating at a constant entropy. There is no change in the entropy. Is that clear? So it will remain the same entropy altogether. So such type of process is called isentropic process. So remember, reversible adiabatic process is an isentropic process. Then, now let us talk about irreversible adiabatic process. Irreversible means what? Q irreversible is 0. Okay, Q irreversible is 0. Now, delta S of the system, how did we define? N CV ln T2 by T1, N R ln V2 by V1. This is how we define. Okay, since it is irreversible, now what I can say, minus Q irreversible by T, that should be defined as delta S of surrounding. But Q, because Q irreversible is 0, this factor is 0. So delta S of the surrounding will be equal to 0. So now what will be delta S of total? Delta S of total will be delta S of the system plus delta S of the surroundings. Okay, so therefore delta S of the total is same as delta S of the system, and that has to be greater than 0. So this is irreversible adiabatic process, everybody. So look into it. Now there is one very important thing. I cannot say this delta S of the system, which was operating earlier in a reversible process, was 0. Since this is 0, now I can't say that delta S of the surrounding will be 0. Sorry, delta S of the system for irreversible will be 0. You cannot say that, sir, it is a state function. Problem is, yes, it is a state function, but you will never be able to achieve all the dimensions same or any one of the dimensions same with reversible versus irreversible. So therefore, in case of irreversible, delta S of total is equal to delta S of system, which is greater than 0. Correct? This is what you will notice. Guys, please check this out. If there is any doubt, let me know. Otherwise, we'll go ahead. What if you have a free expansion? Free expansion, we have learned it earlier. In case of free expansion, work done is 0. Heat given is 0. So it is irreversible adiabatic. Delta U is 0. Delta H is 0. Delta T is 0. These are all the conditions we know when it comes to free expansion. And now, imagine an ideal gas is present at pressure P1, volume V1, temperature T1. Okay. And then this is, there is an external source here and there is nothing outside, everything is vacuum, so there is no external pressure as such. So in that case, naturally what will happen, this gas will start trying to expand on its own. So irreversible isothermal plus adiabatic process. So for this particular case, it is irreversible, it is isothermal also, temperature is not changing, and adiabatic process also. Okay, so delta S of system will be equal to nR ln V2 by V1, and delta S of surroundings will be equal to 0. Okay, because Q irreversible is 0, so surrounding will be 0, but system cannot be 0 because volume is increasing. Hence, delta S of total will be equal to nR ln V2 by V1. Clear? So you can remember in free expansion, if there is anything changing, it has to be entropy of the system. So entropy of the system is increasing. Clear? Finish everybody? Right. Let's solve this question now. Check it out. 3 moles of an ideal gas is expanded isothermally from 2 liters to 10 liters at 27 degrees. Calculate system, surrounding, and total entropy change in 3 different conditions. One is reversible, irreversible, and free expansion. So, starting with temperature T1, sorry, temperature is constant, so delta T is 0. Volume V1 is equal to 2 liters, V2 is equal to 10 liters. Temperature at which it is maintained is 100 kelvins. So now delta S of the system will be equal to NCV ln T2 by T1 plus NR ln V2 by V1. This is the general formula. And now since temperature change is not observed, so it has to be only NR ln V2 by V1. So delta S of the system is equal to 3 moles. So 3 into R into ln V2 by V1. So which is 10 by 2. So it is 3 into R into ln 5. So this is equation 1. Put this as equation 1. Okay. Now what about surroundings? Delta S of surrounding, if it is reversible, so it has to be minus delta S of the system, which is equal to minus 3R ln 5. And delta S of the total has to be equal to 0. So this is for case 1. Okay, this is for case 1. Let us do it for case 2 now. In case of case 2, it is irreversible against constant pressure of 1 atm. Okay, external pressure is given as 1 atm. So you can see here also delta T equal to 0 because it is uh, isothermal, and I can say that delta S of the system which is operating reversibly has to be minus delta S of the system if it is doing irreversibly to finally go to the same volume. Okay, so in that case delta S of the system irreversibly will be equal to same 3R ln 5, while delta S of the surrounding will be equal to, right, minus Q irreversible by T. It has to be minus Q irreversible by T. Clear? And now how much that will be? How much will be minus Q irreversible by T? Okay. Now notice this one. When it comes to Q here, because it is an isothermal process, delta U will be 0. If delta U will be 0, this Q irreversible will be equal to minus W irreversible. So work done irreversible will be equal to minus Q irreversible. So therefore, delta S of the surrounding can be written as W irreversible by T, and W irreversible can be written as minus P external into delta V by T. So which is equal to external pressure is given 1 atm given here, right? So that into final volume is 10 minus initial volume is how much? 2. So how much it is? 8 atm liter, correct? And this will be the work done, and that divided by T, right? Minus P external by T. T is how much? 300. Okay. I can put this as atm liters. If you notice that, uh, I can put this in joules, as 8 into approximately 100 by 3. So which is 8 by 3 joules per Kelvin. This is approximate value for delta S of surroundings. This is in the second case, everybody. So you can notice that delta S of the system, which is equal to 3R ln phi, that is not changed. While delta S of the surrounding, we just found it as 8 by 3 joules per Kelvin. So what should be delta S of total? It has to be 3R ln phi. Okay. And notice this one. So here minus should be there. So this is actually minus value. This is all minus value. So that is equal to minus of 8 by 3. So this will be the case, and it has to be greater than 0. Even after solving, you will get the same thing. Please go through the two cases here. I hope irreversible case is clear, everybody. Finished. Second one is clear. Right. See. Now what about the third one here? Third one is free expansion. So if it is free expansion, delta S of the system is not going to change. That will still remain 3R ln phi, because we are talking about the same volume change. Delta S of the surrounding, which is equal to minus Q irreversible by T. Outside there is no heat, so Q, this will be 0. So delta S of the total, delta S of the total will be same as delta S of the system, which is equal to 3R ln phi. So this is the value. So I guess the total question is clear, everybody. Sorry. Finished? Finished? Everyone? Right. Let's see the next one here on a similar lines. 2 moles of an ideal gas is expanded adiabatically this time. Okay. Earlier it was isothermal. Now it is adiabatic. Adiabatic from 10 liters, 27 degrees Celsius to 80 liters. Okay. Calculate delta S of the system. Again, first if it is reversible, second it is irreversible, third it is free expansion. Got it? Everybody, let's solve it together. Check it out. First one being reversible. For reversible process, check out. For reversible process here, what are the factors given? N is equal to 2, and we know that delta S of the system, okay, because it is adiabatic process, you know that Q reversible by T, Q reversible is 0, so delta S of the system is 0, delta S of the surrounding will be 0, delta S of the total will be 0 because it is an isentropic process. So this will be your first case, which is reversible case. Yeah. Now let's talk about the second case. Second case is when it is irreversible. Okay. So if it is irreversible case, you know that from what volume it is going to what volume and what was the initial temperature. Now, so we need to first find out what is the final temperature. So to do that, what I will do, see, you know that delta U is equal to Q plus W. Okay, Q irreversible plus W irreversible. This is for irreversible process. This is for irreversible process. But Q irreversible is 0 this time. So in that case, delta U will be equal to W irreversible, which implies delta U can be written as NCV delta T, which is T2 minus T1. That is equal to W irreversible. W irreversible can be written as minus P external into V2 minus V1. This is what we can write. And you know that final pressure will always be equal to the external pressure. So that implies NCV T2 minus T1 is equal to, this is P2. So if at all I take it to the, if at all I take it inside, I'll get this as minus P2 V2, and this will be equal to, okay, plus P2 V1. This is what we have. Okay. And since it is an ideal gas, we know that P1 V1 is equal to nRT1 and P2 V2 is equal to nRT2. Let me use that value here. So this implies, I can write it as NCV T2 minus T1 is equal to, this can be written as minus nRT2 plus P2. Acha, P2 can be written as nRT2 by V2 into V1. This is what we can write. Okay, so NR will come common in both of them, and CV, if you notice that this is given for monoatomic gas, so CV value is given as 3 by 2 R for monoatomic gas. So if I substitute that, this R and R here right hand side will get cancelled, N will get cancelled. So what do we left with? We'll be left with 3 by 2 into T2 minus T1 is equal to, NR is lost from here also. I'll get this as minus T2 plus T2 into V1 by V2. This is what is left over. Okay. So we will get this as 3 by 2 T2, right? And plus T2, clear, minus T2 into V1 by V2. That is equal to 3 by 2 T1. So from here, V1 by V2, how much it is? Originally volume was 10, now it is 80. So V1 by V2. So therefore, so 3 by 2 T2 plus T2, which is 5 T2 by 2. 5 T2 by 2 minus T2 into V1 was 10. Okay, V2 is 80. So it is 1 by 8. So this is 5 by 2. 5 by 2 T2 minus T2 by 8. That is equal to 3 by 2 T1. So which is equal to, so we will get this as 20 T2 minus T2 by 8 is equal to 3 by 2 T1. So this goes 4 times. So if I take it to the other side, 20 T2, sorry, 20, this will become 19 T2 is equal to 12 T1. So T2 will be equal to 12 T1 by 90. Okay, please check it out, everybody. Sure got that. Now what about the third one now? So when it comes to third one, it is free expansion. For free expansion, you know that again Q irreversible. This is 0. It is an irreversible expansion. Delta T is also 0. So delta S of the system only depends upon one factor, which is NR ln V2 by V1. And this values are given to you already. And delta S of surrounding will be equal to 0. And delta S of total will be same as that of delta S of system. So which is equal to NR ln V2 by V1. That's it. So this is about free expansion. Done? Right. Now, whatever we discussed was about entropy change for an ideal gas. Okay. So see the second case. What if it is entropy change of solids and liquids? Got it? By definition, we have discussed this as Q reversible, correct? But this heat which is been given can be represented as ms delta T. Okay. And usually for solids and liquids, we consider that the mass and specific heat values are constant values. So if this is constant values, and then you integrate this from T1 to T2, so we can say delta S of the system will be equal to ms ln T2 by T1. Okay. So if it is for molar entropy, this M should become molar mass. That's it. For solids and gases, Cp, Cv, everything is same. We can simply write it as Cm here. Okay. Clear. Now, notice this case. As an example, you can notice this one. Suppose I have two metal blocks connected with each other, like this. Two metal blocks are connected with each other. One metal block is cold, the other metal block is hot at Tc and Th temperatures. Both has mass m. Both has mass m. Both of them are made up of same material. They are not different either. Okay. In that case, if at all I want to calculate delta S of the system, how will I do that? See, total change of the, because this entire thing is our system. Okay. So within the system, you can notice that there is an entropy change of the cold body, there will be entropy change of the hot body also. Okay. So if this is temperature Tc and this is temperature Th, the heat will keep exchanging till both the side the temperature becomes equal, correct? And how much is that temperature? Final temperature, okay, so T average will be equal to Tc plus Th by 2, because both of them have same masses. We don't have to change much. So simply the average final temperature will be equal to Tc plus Th by 2. Okay. So now delta S of cold can be written as Ms, ln T2 by T1. This is what we have learned from the above, uh, from this above formula. You can see Ms ln T2 by T1. So I'm writing this as Ms ln T2 by T1, and this is mass M into S into ln. For cold case, if you notice, the final temperature is this much. Initial temperature is Tc. So therefore, Tc plus Th divided by 2 times of Tc. This is formula 1. Similarly, delta S of the hot body will be equal to Ms ln T2 by T1, which is equal to M into S into ln. Now, T2 is the same thing. We will get this as Tc plus Th by 2 into Th. This is for delta S of total. Now, if I add both of them, delta S of total will be equal to cold plus hot. So, Ms will come out to be common into ln Tc plus Th whole square divided by 4 times of Tc/Th. So remember, this is the formula. This has been asked many times. J, please check. Everyone, let me know if you have any doubt there. See the next case. The other case which can be asked here is when you have two different gases mixing with each other. Okay. Suppose the container volume is this much. This is VA, this is VB. The total container volume is VA plus VB. On the container A side, we have Na number of moles, pressure is P, temperature T, volume E will be VA. Similarly, number of moles of B, pressure temperature is same, VB is different. Now mixing both of them, that means you remove this compartment, what happens? Both of them will got mixed. Pressure and temperature remain same. Okay. I need to find out what will be delta S of the system. Okay. So obviously this gas must have spread, so its disorder has increased. The B must have spread towards A, so here disorder of B must have also increased. So delta S of system will be delta S of A plus delta S of B. Okay. Now you notice what is delta S of A? Delta S of A, because everything we are operating at constant temperature, the temperature term won't be there, only volume term will be there. So NAR ln V final by V initial. V final is the total volume here, that is VA plus VB. And delta S of B, B will be equal to NB ln VF by VB. So A can be written as NAR ln V final is VA plus VB. So this divided by VA and this divided by VB. Okay. And check it out. the mole ratio, the volume ratio or the mole ratio will be same here. So mole fraction or volume fraction, Va by Va plus L, Vb is equal to Na by Na plus Nb. That is equal to a mole fraction, isn't it? So I can write this as 1 by mole fraction. Here also I can write as 1 by mole fraction of B. So Na ln 1 by Xa, which is a mole fraction, and delta Sb will be also equal to the same case. Now the total entropy change will be equal to delta A, delta Sa plus delta Sb. So when you bring this Xb on the numerator, this will become minus. So that's why the minus R is carried forward and you will get Na ln Xa plus Nb ln Xb. This is how you can calculate the entropy when the mixing of gases has been done. Please check quickly, everybody. Whenever there is a reversible phase transition, okay, what are the reversible phase transition means? Where there is a change in the state. For instance, uh, if I take the triple point of water like this is the triple point of water. This side we have solids, liquids, and gases. Clear? So when there is an equilibrium exist here, we say there is a state transition. Here also there is a state transition. Okay. So these lines represent the equilibrium and it is plotted between pressure and temperature. Okay. And now that's what we are trying to do here. Check out. Always it is isothermal and isobaric. Reversible phase transition is always isothermal and isobaric because phase transition always happens at a constant pressure and constant temperature. Okay. So if delta S of the system at constant temperature and pressure is taken, the if you provide Q amount of heat, so Q reversible by T, that will be the heat given. And at constant pressure, whatever the heat that is given, that will only change the enthalpy of the system. So hence, Q reversible can be now written as delta H of the, which is enthalpy change of the phase change, that divided by T. Okay. T is the transition temperature. Okay. So if it is going from solid to liquid, so that is the transition temperature we are talking about. So in that case, that will become fusion temperature. If it is liquid to gas, it is boiling point. So one is melting point temperature, the other one is boiling point temperature. So you can see here H2O when it is in equilibrium with H2O liquid, delta H fusion, if temperature is 0 degrees, that will be the melting point. So delta H of fusion will be equal to delta H of fusion by 273. Same way, liquid to gas, it will be vaporization. Temperature is 100 degrees Celsius. So pressure is 1 atm. So delta S of vaporization is equal to delta H by T. So delta H of vaporization by 373. Okay. You can do the phase change even when you have allotropic change. That is, a gray tin is changing into a white tin. So delta H of allotropic value. So delta S of allotropic is delta H of allotropic by transition temperature. Okay. So I think this part is clear. Now notice there is something called Trotton's rule. Okay. This is the ratio of molar heat of vaporization of liquid at its normal boiling point is approximately the same for all the liquids and that is equal to 88 joules per Kelvin. Got it? Clear? So which means the entropy change, I'm talking about the entropy change. The entropy change of almost all the liquids, correct, at their respective normal boiling point comes to be same value, that is around 88 joules per Kelvin. This is called Trotton's rule. So delta S of vaporization is equal to delta H of vaporization by T. It is almost same for almost all the liquids. You can see CCl4, benzene, toluene, CS2, mercury, I2. They all will have same delta S vaporization value. Okay. But by chance, if you have any hydrogen bonding, any strong molar attraction between the particles, in that case, delta S of vaporization will be greater than 88 kilojoules per mole, 88 joules per Kelvin. Like for example, water, ammonia, alcohol, acids, they all will have higher value of delta S vaporization as per Totan's rule. Clear with Totan's rule? Next. Now, before going further into the details of, third law of thermodynamics, first, let me tell you one or two examples how we can get through it. Acha, let me finish that. Okay, it's okay. You can do it either ways. Check. What is third law of thermodynamics means? Okay, according to third law of thermodynamics, at absolute zero, that means 0 kelvins, the entropy of perfectly crystalline substance is zero. That means if you have, because at absolute zero, you will you will see every state will convert into solid state only. And if that solid state is a perfect crystalline substance, in that case, the entropy of that perfectly crystalline system will crystalline substance will be equal to zero. Okay, clear everyone? So one thing, at this point there is no kinetic energy, so there is no disorder in a perfect crystal. Okay, so only when there is some kinetic energy, there is some uh, incorrect arrangement of the particles, then you will see some particles are moving, because of which you will have randomness and hence will have entropy. Okay, so for example, if at 0 kelvins you have a perfect crystal, then this entropy is zero. And if there is any entropy change from 0 to T, so let's say temperature T, then I can write 0 to T Q reversible by T, correct? Now here is the interesting part. Since this factor is 0, I can calculate the absolute entropy at a particular temperature T. So basically, third law is helping us to calculate the absolute entropy of a substance. Okay. So entropy of a substance at temperature T will be equal to 0 to T Q reversible by T. Okay. Now check this out. If you have absolute zero kelvins here, so at that point entropy is zero. But from there, as the temperature starts increasing, right, the entropy will start increasing. Entropy will reach to this point, okay, where it reaches the melting point. At melting point, temperature does not change, but entropy will keep changing. So you can see entropy will increase, and thereafter it has now liquid state. And liquid state, as it goes towards boiling point, from there again the uh, no change of temperature and everything will convert into gas. And 5 to 6 is about gas at two different temperatures. Okay, this is gas at two different temperatures. Clear? So now how do we write the total entropy change from 1 to 6? 1 to 6, what are all the entropy changes involved? Everybody. So please check this out. Delta S of total in that case will be equal to delta S 1 to 2. Okay, because from 1 to 2 here, then 2 to 3, then 3 to 4, 4 to 5, and 5 to 6. Now let us check 1 to 2. 1 to 2, 1 to 2 we have 0 onwards till melting point Q reversible by T, plus here 2 to 3 you will have delta H of fusion divided by temperature of the melting point. So this is the melting point temperature. Okay. Next, 3 to 4. 3 to 4, you have melting point towards boiling point. You're integrating. So it is Q reversible by T. Done. Next, 4 to 5. Check out 4 to 5. 4 to 5, you have only vaporization happening and boiling point is constant. So delta H of vaporization by T boiling point plus lastly 5 to 6. 5 to 6 is boiling point to a certain temperature T and Q reversible by T. Okay. And you see that here Q in the first case I can write Q reversible can be written because it is of solid, right? So we can write it as Cp solid into dt by T. Similarly, here also it is a melting, from this melting point towards a new boiling point here. So from here to here, we can write Cp into liquid dt by dt and from melting point towards boiling point. And therefore, last one, here also there is Q reversible, which is Cp of the gas into dt, clear? And this is from boiling point to any temperature T. Okay. Because you are operating at a constant pressure, we can write it as Q reversible can be written as Qp delta T by T. Delta T by T, I forgot to write T. Everyone clear how to write the entropy change? Check it out. Let's go through that question once.